Although it is just in the beginning, we got already lots of the results as you will be able to see. And they don't work, you can interrupt it in any time to ask questions, etc.
Very good.
Okay, so hi everyone. Let's add Lucas. Well,
No, don't deixa. Sorry, Lucas, go ahead.
so I am PhD student at IAG USP in a way. So I just started my PhD, so I don't have a lot of things to show. So I think it's gonna be a little bit short. But anyway,
But you have lots of things to explain to people that like me that don't know this.
so ask questions. Yeah. Good. Okay, so let's start. How can we define a physical one-dimensional galaxy cluster? And I think that the main answer would be like, oh, could it be the visual radius, for example, or the 200? 200, I think everyone knows the radius of a sphere that encloses 200 times the critical density of the universe, or the matter density, in a way. And this is the traditional way to say what is the modality. But all these traditional ways that have suffered from the same effect. That is the pseudo evolution. So it's okay if I can see here.
Can you go a little slower because so how do you measure the mass of the so you said the R200, which is
Okay.
the radius of that encloses a sufficient mass that's 200 times the average density of the universe.
Yes.
How do you measure this?
How to measure the mass?
Yeah.
From the models, like I'm using here, weak lensing measurements. So, you know, you look in the galaxy in the field and see the elongations and have also the elongation depends on the mass of the lens. We have the mass of the cluster, and you can have the radius of this.
Is that so simple? Because it depends on geometry.
We have to assume that it's a spherical things with it. Works.
All elephants are spherical.
All the cows are spherical. Elephants also. Cows and elephants. So okay, so you're making some assumptions, but okay.
Yeah, they just that traditionally, this is the two ways to define one diagonal cluster: the visual radius or the R200.
What's it, the first one?
Visual radius.
Video
In the
radius.
visual terrain that you have to.
So what is the? I'm sorry, I don't know much about this. What's the video radius?
Do you know the visual terrain?
Yes.
It's just this. You estimate the expression of the cluster, and you calculate the mass, and you have the radius.
Okay.
Okay, so this both are the typical way to define one diagonal.
Okay.
But that's a problem. That is the pseudo evolution. What happens is that both the weights that we're talking about here depends on reference density. Like I'm saying that the spread that encloses 200 times the critical density. So the universe expands, the volume increase, and the density increase.
Yes.
So the mass will increase as well. Even if the cluster did not accrete any matter, the mass will increase. It's not physical. It's just something that comes from our definitions. Like, one point, right?
What mass increase?
The radius increases.
The radius increases and as well the mass, because
Yes.
from the models, we have just
The mass inside this radius.
Yes.
Yes. Because of the gravitational collapse of the living.
No, it's in fact from the definition, because the density will decrease. So to have
The average
200
density of the universe will decrease.
Yes.
But the
The
density
average
inside the
density
cluster maybe increases, no?
No, the definition of the critical density, for example,
Yes, that I
Yes. it will decrease.
Yes.
And the masses they are talking about here come from these definitions.
The mass inside the cluster
Doesn't change.
change.
Yes. The density
Okay.
changes, but the mass doesn't.
The R200 change.
Change.
Due to the change in the reference density.
Right.
So it's a pseudo evolution because even that with the mass kept constant,
Right.
due to the stretch of the universe, due to the fact that the critical density decreases and the R200 is defined as the radius that contains 200 times the mean density of the universe. This implies in a pseudo evolution of the radius of the cluster.
By this definition of R200.
Yes,
Yes.
to this definition.
Yes. So it increases because the
Because-
density decreases.
Huh?
The R200 increases because the density, average density of the universe decreases. So
Yes.
it takes more radius to get to 200 times
Mhm.
the average density.
And that.
That's what you call pseudo.
Okay,
Thank you.
there's a plot here, I cannot point anything, but this is the evolution of the model in radius and mass. And you can see that from
Maybe you can point. There was a way of pointing. It's not this point.
You use the mouse, maybe you can point.
You know, the mouse can.
Okay. So you can see here, you can see that for example, redshift 1, we have a mass here of it's a halo and a halo, 7, 10 to 11, I think.
Yes, then to the.
And it's a point, it's a simulation, and you say that okay, this halo is not accurate any matter. But as the evolution, as the time passes, we see that how as the reference density decrease, the mass increase because of the radius as well.
I see. So this increase in the mass is not because it's accreting anything, it's
It's
just
not
because
just
radius is larger and you're taking more of the average density of the universe.
yes.
So it's very small. That's why it's okay.
So it's a problem because the effects of the measurements and our definitions, our understanding of the formation and things like that. So that's why we're going to talk about the splashback radius. What is splashback radius? Going straight to the point, it is the first orbital center of accreted matter.
What's apocenter? Sorry, I don't know.
It's the maximum distance that you have a cluster and have particles falling into the cluster. It'll pass to the center, but it loses an energy because of dynamical friction. We come back. So the maximum distance is the epicenter. Okay. So this distance is the splashback radius.
So we're assuming that the cluster is accreting matter.
Yes. They always are, but
They always are.
yes. So this splashback radius is the first orbital center. And that's okay. This is again simulation from our 2021. And each line here represents our particle. As you can see here in the y-axis is the time. So a particle comes from a higher distance, go to the center, and splashbacks. It's good again for higher distance when it comes.
It should go through the center and back, no?
Yes.
So that's what
because it's truncating the
it's
not having
truncated.
negative values. Yes.
So it goes that way and then goes back. But
Yes.
you're truncated in the center. This plot
So
is
it's in the center because not have a
It's a radial plot.
it's a radial plot.
so this apocenter for every particle that is found in the cluster is the splashback radius, the mean of this. The idea is that this radius can serve as a more physical boundary of the cluster because it will separate the region that is found in the cluster and the region that is in orbit of the cluster. Okay.
I think I understand now. I don't understand how you measure this, but
Oh, yes.
Just additional point. As the galaxies fall into the cluster, they go to the splashback radius, and then this creates a caustic there. I don't know if you're going to talk about the caustic or not.
so you have a larger density in this.
So there is an increase in the density.
It's like a
over there.
ring that has increased density.
Yeah, but we detect it more through He will explain how it actually is. It's amazing that it works. You can use.
So the idea is that this radius doesn't come from a definition, so it doesn't solve for the evolution, which is really good.
I agree. In effect of the evolution.
So how to measure it? So as I said, it can separate the following regions and the part that is realized in the center. Okay, so you can imagine that it's gonna be one able term in the center, one model, one density profile in the center, and another that's in the following. So the idea is to describe this model is as two profiles, two models of the density. Okay.
So it's a two halo model. So
Yes, two model. So here we have the part in the center, the origin part, the origin region, the infalling region, and the total. So you can see that we have in the center a profile that's kind of truncated, goes to zero really sharp. We have an infalling part, infalling region, and in the total, what happens is that like a jump, a density jump in the region of the splashback radius that separates infalling in the origin parts.
but these plots are just measurements of the simulations.
Yes.
But it's not model yet, right?
No.
Yeah. Okay. So what's the difference? You have to, okay, so you have to separate somehow what is orbiting, what's in falling. Yes, you have to separate that in the simulation. Right?
Which we can do it because in real world we will see just the total.
Just the total.
But that is to model with two components. Okay. So that is we can model. We can have a model. Let's say I have one halo model that's intricated and a two halo model, and I'm gonna describe it just like this. And as is a jump here, jump density, when I look into the slope profile of the cluster, it's gonna have like a sharp drop, really in the special radius because of the jump.
Right, so in the simulation, you can see this. So this drop in the first
Yes.
plot, this is the splashback, right?
Yes.
And then you have an increase also because of the caustic.
Oh, the logic is because we have like almost continuous part here that's in the infalling regions,
Yes.
and then we have like a drop in the outer parts.
When you select the two.
Yes, so
So what you call the caustic is this little thing here? It's this thing?
yes, that appears marked like this in the slope profile. So we can use this.
So it's actually a drop.
Yes, drop. So we can use this drop as a proxy to make this special.
With the truncation in
The model.
the slope, right, the first day.
Yes.
Okay.
Actually, sorry,
Next.
as you will show, to model this sort of thing, we need to introduce a truncation in the process. Yes. Otherwise, there's a.
So I'm gonna say how I do this. Actually, what happens in the literature is that people used to model the density profile clusters as a course density, the real density. But you can think that it's really noisy because even when you go to hyperchips, like for example,
Yes.
we start with faint galaxies, and it's difficult to measure and it's difficult to model. So actually,
Can you just go back? So in the plot on the right, there's some letters that I know. I think I remember what the Navarro Frank
Yes.
and White profile is.
so what's it shows in here is that it's not minus from future. is the, what's like said, is the W and Astro profiles without the calibration. So the sharp here is a little bit more smooth. And this red one is with calculations. So you can see better.
But I thought the Navarro black and white were always decreasing with the distance.
Yes, here is the numeric white, and we
okay.
have in 1.5 and the 2 halo.
Ah, so this is already adding up the
Yes.
infall. Ah. So it's Navarro black and white plus the falling part.
Yes.
And they're modeling the falling part. This is from a model now, the falling part is from a model or is
Yes.
from this?
Both of our models. Here just showing the example one.
Okay, so there are models that Navarro black and white I know, and then there's another model that
Yes.
takes the falling part into
Look,
account.
here is just an illustration,
Yes, yes.
because we don't model the external region at all.
Okay.
As you use.
Okay.
So what I do to avoid it, to use the number density profile is use the cumulative profile. It's pretty okay. So the cumulative is that we have just a integral here in the density profile. It's number density here. So the integral is going to be the number of dots inside the ranges. And I can measure this. So here are my plots. I did it for my cluster just so as an example.
So sigma is the density. What is sigma?
Sigma is the density, it's a model.
Surface density.
It's surface density, right? So
Number density.
it's number density
Yes,
by volume or by surface?
by surface.
By surface. So you're integrated over a surface with a given radius.
Yes,
You find the cluster center and start integrating from center.
Yes. So it's a,
Counting galaxies.
it's like a 3D integral
to
Yeah,
get
this.
to this. But you're integrating.
Yeah, the radial, it's in projected radius, and an integral in projected radius. I mean, you count galaxies within a given circle. Of
Yes.
this given radius.
Yes. Yes.
This is essentially what this N means.
Yeah, I'm digesting slow. Okay.
But this is very straightforward. Just,
No, it's just that I am very slow, sorry. What can I do?
but anyway, it's really clear that a cumulative profile cumulative distribution is really more robust than a density number profile. So what happens is that this is a cluster, a real cluster. I use just this example. Modeling the cumulative profile and the number density profile, you can see the difference in the splashback definition.
So when you say a real cluster, you mean real data?
Yes.
Oh. So you can measure this using weak length again.
No, just
I'm just counting. It's just
counts.
counting.
Yes.
Yeah. Just counting. It's much easier.
Yes.
So are these plots using real clusters?
Yes. This is MK333.
Okay.
So we have some models to test. And
Sorry, but you don't count dark matter then. Sorry, just saying.
no, let's just take out positions as a
90% of the mass is dark matter.
yes. But can we imagine that the gas position is going to be distributed in the density profile of the dark matter? So we use it as a proxy to map the density
Okay,
profile.
so this cumulative density profile is probably not the whole mass because 90% is dark matter, but it's a good proxy.
Yes.
Okay.
The mass will come in the end.
Okay. This is just numbers.
It requires calibration.
Okay.
Okay, so we have to test some models. We have a lot of different literature. For example, Halo, we assume there's one here that from GBH 2023. It's a good one. we tested others, but it's the best. And from the one halo two, the part that is origin, in center part, we test two models, the SASC and the Lamarck white. Both truncated models. Because remember, the first bed is discovered of superior models. Okay.
I'm slow, I'm slow. And taking some time. So this is the profile, right?
Yes, the model.
This is the outer profile.
And what is this? This is a sum or this is?
This is a parameter.
This is a constant.
Yes.
Okay.
Yeah.
Okay.
If you see as the radius increase, the first term
Yeah.
inside brackets goes
It's down.
to 0. So this is the field density, as we call, the mean density outside the cluster, far away from the cluster.
Okay. So this is good far away from.
Yeah, that's, anyway, this is a parameter that we fix.
Right. So the parameters RT, this RT, which I don't.
Yes, RT, this gamma,
So T is for turnaround, not what?
T for truncation.
Truncation.
Yes.
And sigma m, which is this constant, and gamma. Okay.
Yes.
Okay. Thanks.
You then have the one halo model, truncated. We use the SASC and Lamarck white. That's both of the models.
Okay.
The SASC with truncation function, and as well the Lamarck white. Okay, can I show you how the behavior of this profiles? The two halo, the outer halo, and the SASC and the Lamarck white. They are pretty similar. Okay. So this is how really fast about the data that I use. I compile some tables of clusters with weakness and mass measurements because I want the mass, and weakness is a good way to get mass because we don't have to do assumptions about the dynamical state of the cluster. So I choose these ones. I'm using Cortex, XXL, CCCP, and the Comality. And for the cluster itself, I use the SSS structure, it's the trust for me. And I applied some cuts. I only take clusters in this range of redshift and in this range of mass. Okay, just I share the distribution of mass and the redshift. Yes. And
Now,
now,
how many clusters you have? Selection.
in the beginning, it was like I think 500, but I did the cuts and I only take clusters that I have coverage in SPSS. So I ended up with 200.
So can you go back to the instruments? So this is the mass of the clusters.
Yes.
So 10 to the 15, 14, 15.
Yes.
So each cluster is more than 1,000 galaxies.
Yes, should be, but
Few thousand.
if it is a little bit high redshift, you cannot see all the galaxies. So
Yeah. So how do you estimate the mass through the density?
no, I just took it from the literature and not estimated it.
Okay. So how do people estimate the mass of
The
cluster
length.
from local motion?
You usually use photometry to do this, and because you
You
can,
trace the mass with light.
yeah, so you just see the elongation galaxy in the field, and
So that's the total mass, or is the luminous mass?
no total mass. You put the galaxy and dark matter, gas.
So very naive question. So you have your model for the one halo and two halo,
Yes.
which has some parameters. The question is, these parameters, they depend on the cluster or they are independent of the cluster?
Depend on the cluster.
So each cluster you have to fit these parameters.
Yes.
Yeah, okay, that makes sense.
Look, it's interesting to note that we are teaching an integrated profile with lots of parameters. So you can wonder, how does it work? Because it's not obvious that when we started the project, it was not clear at all that with so many parameters, we would be able to obtain meaningful results. Let's wait and see.
Because each cluster has different parameters, no?
Yes, yes. But there are some regularities, of
Yeah.
course.
Yes, okay.
So we're going to share some preliminary results. It's really in the beginning, so some things. The first is the model selection. I said that I was testing the SASC and the apartment wires. So what I did to test is I did statement profiles because I could increase the silent noise and it would be better. So I stacking the profiles in bins of redshifts and mass. Here I'm showing all the profiles that I have. And driving redshifts. And to stacking them, I have to normalize. So the profiles will be in the same scale. Okay. So I normalize in the radius distance for the center by the I200. I also in each process I cut magnitude by a magnitude of 19.24. That is kind of 21 in our redshift in the same. I also took an interval of 3 sigma. Sigma I'm calling is the closure expression of the cluster. And for the number, for the motif number, I normalize by the background. That is just the this parameter here, sigma. I actually can measurement this in the survey. I can just take some random points and estimate the density in the survey, in the field. I have this parameter. So I normalize them for each cluster. So basically, I have the parameter, I calculate the background, but just look at this. And I can have the number of galaxies in the field. And normalize it by the I200 as well.
So what to understand is that, so R is the distance to the center of the cluster.
Yes,
Normalized in the,
normalized by the I200.
what is R200 say again? So like,
You were not here in the beginning, but explain what was it?
yeah, sorry.
I200 is the radius of a sphere that encloses another density of 200 times the density of the matter density of the universe. So it's just a way to
And
determine a quantity of
that is the number of galaxies in the row.
number of galaxies inside our radius.
Okay.
Okay,
And the color code is,
redshift.
yeah, okay.
Okay. So I do the stacking and finding the profiles, right? So here I'm buying in redshift. So in the first line, first rows is from redshift 0.01 to 0.23. And then so, and in each column, I'm buying by the mass.
So in previous plot, it had this large dispersion.
Yeah, I was just showing the
And then-
equations. And here it is stacking.
And then, okay, so
The
You just bring your redshift.
Yes. So I did the stacking and fit both the SASCI and the network profile to see how could perform better. But I actually increased the confidence interval by a factor of 20 to 10, and you cannot see even like that because they are pretty similar, but it doesn't change too much. Here I'm showing
sorry, the errors are just Poisson errors or
yes.
just Poisson, right?
Yes. Here I'm showing some metrics to see what model could perform better. Here's the Q square, the AIC and the VIC. But there's not a big difference between them. Anyway, the SASCI seems to outperform a little bit the graphic wise, but nothing that really matters. In any sense, it's actually use the SASCI. Just that. Good. And now we have the model. We aim to see how the model is affected by constraint selections, like the magnitude limit, the maximum range that I do my fittings, something like that.
Just a curiosity. So you have lots of parameters, right? For each cluster, you have. And then you have this chi-square, which depends on all these parameters. How do you find the best fit? Just curiosity, what? You have a function of several variables. The chi-square depends on all the variables over most. So it's a very, just curiosity, because we have also these problems when you do cosmological analysis, you have to find the best fit. And sometimes it's difficult to find the minimum of this function that has many variables. So what is the code that you use?
I was using Markov chain,
It's a Markov chain Monte Carlo.
but I changed it because I saw that it's too
Too slow.
slow. I'm now using just least squares.
Steepest descent or something like that.
So, most informations. The first one is the magnitude limit. I want to see if I change the magnitude limit and change the splashback radius that I get. So, like, I'm gonna put a cutoff magnitude limit that is 22, minus 22. It will change if I put cutoff 20, minus 20. And that's not right here. It's what odds the special here's individual clusters now. It's my samples of clusters. The splashback radius that I estimate for them, normalized by the I200, and here by the magnitude limit. So you can see that it didn't change almost anything.
Sorry, what are the dots up there in those boxes?
Here, yeah, outliers.
Yes.
Oh,
So you have 4 clusters with 4 main clusters that are outliers.
yes. From my 200 to okay.
So each cluster has its own splashback radius. So what you're plotting here in this green, for instance, what is this? Sorry,
Even
Explain what it means the box.
yes, I
Okay,
missed
but
that. Yes.
here in the center line is the median. It's the median of this distribution. The edges is continuous, like 20, 25 and 25.
Okay.
Here are the lines. And here's the maximum power.
Maximum and minimum. Okay.
Maximum minimum.
Result.
Okay, thank you.
Lucas, did you check the properties of these outliers?
No,
There is any,
it's the time.
I got it, yeah. Maybe it's an interesting.
Yes, but it's okay. It's 2.5 times the 500. It's okay. It's
Yes, of course.
in the interval of 1.5 radius.
Yeah, I agree, yeah. But maybe there is some convergence in the properties of this cluster. I don't know.
What is the same
correct.
outlier located? It's the same point there. I mean, the one that's showing that the highest magnitude beam, same that is also showing the other one, right?
I did not check whether. I think so.
And on different outliers, it's the same.
Yeah, it's the same.
Mhm.
The maximum radius. So I'm doing modeling, and I can decide if I want to go to 1 megaparsec, 2 megaparsecs, 5 megaparsecs, and things like that. So I want to see if it changes the radius as the maximum limit. And again, I do the modeling go up to 3, 500, 5, 500, and 8 megaparsecs too, because in the real situation, I will not have the 500. So I have to test this inside as well. So, I kind of see a trend here. I don't know. Maybe. But maybe. I have no idea. I didn't show it flagged yet. So,
Would you expect a trend?
no.
Look, we didn't know what we expect.
Yes.
We are exploring the problem and looking for things that might affect our estimation in the end. What is for me, what I think of this is that we need to choose, say, 5 times R200. Because you can see a trend, you can see variation, but the variation is not tremendous. So if we choose a value, say 5 times R200, then we can continue with that and do the next steps using these ranges. Because you can calibrate at the ranges that you want.
Now the center definition, I have to define center of the cluster, and we have a lot of different ways to do that. The first one, the most common is the BCG, the private classical divided cluster galaxy. We also have a geometric center. We can do a median or a mean of the all positions of galaxies inside the cluster. And sometimes you have the X-ray emissions. Emission, you can have the maximum emission at some point, you can define it as a center. Can show an example, it's for common cluster. So the XG is in black. The lines here is the level in black is the X-ray emission. And in this case, the X-ray and the XG are pretty aligned.
With lensing, can you also see the center, the mass center of the cluster?
I don't know what you can see.
Yes, but maybe not with such a resolution.
And in yellow here is the geometric center. It has a little bit offset. So for the ECG in the X-ray center, it's pretty the same. But something happened to the geometric center, it's really higher. I don't know if it's a real problem because geometric center are not really used. It's kind of not the best choice. So I don't think it's a problem, it's just something that's good to know. Anyway. And finally,
In the end of the day, Lucas, I don't think that this is a problem because we'll be able always to use the X-ray center after a Rosetta data. I don't know if you are aware, but there's a survey by a German-Russian satellite called Rosetta that is mapping all the sky in X-rays. And X-rays are excellent to detect the real galaxy clusters because most of the variables in the clusters are in the form of a hot gas that emits in X-rays. And so it's useful not only for identifying the clusters, to estimate cluster methods, etc., but also to discriminate between false cluster detection, because you can detect, say, a galaxy overdense in a given region that might be just a result of the line of sight, objects in the line of sight, without a real physical structure, without being a real physical structure, and the X-ray avoidance problems.
yeah, the only problem with X-rays is that sometimes they are disturbing, the gas are disturbing, so the center is not really aligned with the minimum potential of the cluster.
Yeah, but in this case, everything will be any measurement, except of course with lensing, will be affected. But center, in the case of disturbed cluster, is not very meaningful also.
So these clusters that can be found in CMB synapse is that useful for this? Or
Yes, probably most of them are detected as
but for the center, locating the center, don't we-
yeah,
Resolution enough,
right?
like X-ray.
yeah. These measurements in X-rays, they have an accuracy of arcseconds or a few, 1 arcminute at most. Very precise.
Finally, the branch interval that I'm choosing for the cluster. So it's a little bit, actually it's a little bit confusing. You can see I like green. Anyway, this big square here is if I'm choosing like 5 times sigma velocity expression. But if I can also choose 3 times this the velocity expression, and I can choose like a caustic. I can use a caustic from Jafet 2015. Caustic is just a way to try to clean the contamination in the cluster. And yes,
But acoustic is an increase in the density. That's
oh no, different questions here.
oh, this is additional cost.
Yes,
So what is this cost?
I didn't have what here, but it's the cost is comes from gravitation. So it's just
From?
gravitation. So it's just the square GM by R. So it's just the
The physical.
velocity scale.
Okay,
It corresponds to the escape velocity of the cluster. So galaxies outside, of course, those projected in the green band, they are cluster galaxies and also galaxies projected in this direction. But if you measure the velocity, this is what people call the cluster phase space. Because here is radius and in the vertical is the relative velocity, relative radial velocity of a galaxy with respect to the cluster mean. So yeah, you can see this in this form. The limits correspond to the escape velocity of the cluster. So people reject the objects outside this region because probably they are not linked physically to the cluster.
How do you know that the galaxies you see inside the cluster, they are realized and they're not just passing by? You assume they're realized?
Because we are seeing something truly is projected, so we cannot say, oh, it's really inside a cluster or it's not. Just
You can say for individual object, but you can say statistically, because you know when you model mean contamination also, the background density. So you subtract this from everywhere. So you have, say, statistically is what you expect. Of course, for individual objects, if you have the radial velocity, okay, you can say whether it's a cluster member or not. But otherwise, you can rely on statistical standards on.
So the dispersion velocity is just the average of the transverse velocity that you can measure.
Yeah, we assume it's not physical as well, because radial velocity, of course. But not for the velocity, well, this work doesn't use dynamics, but when you do dynamical modeling, you can assume anisotropy also of the radial velocities within the cluster. Well, but it doesn't appear.
Okay, but the dispersion you do measure.
No, for some galaxies only, and for some clusters only. That's the problem. Because, if we have radial velocity for many cluster galaxies, we have a way to estimate cluster masses that is the virial theory. Every gravitational system in equilibrium obeys the virial theory. That is relates, say, velocity dispersion as a kind of pressure with the cluster size and the cluster mass. So from sort of thing, you can estimate mass through this approach. But unfortunately, spectroscopy is very expensive from the observational point of view. So we don't have measurement of velocity, radial velocity, or even velocity dispersions for any clusters. There are many surveys going on that plans to measure the cluster dynamics for hundreds of clusters in the local universe. We are members of a collaboration led by Sheeran colleagues that aims to do that, using the foremost instrument of the ISO observatory. But this should start next year.
so I'm to the end. Now the finally is my speech. This is really preliminary. It's in the beginning. So this one we get not. We have the spatial ranges and the mass. We join the mass. The idea behind why we are doing this is because as I said, masses are really expensive to measure. We have immediate replacing elements or spectroscopy or X-rays, for example. So have a relation, a scale relation from easy parameters that can observe is good to measure mass. And as you know, the mass, the definition of mass can put constraints in the cosmology, in the mass parameters, human age, like that. So it's important to have mass, and when it's expensive. So it needs to have this type of scales. Now we got a expression of 0.3 dex, but it's kind of related comparable to other explanations like luminosity or X-rays and richness. But it's just preliminary, and I said that I'm using spectroscopy. So if I have spectroscopy when I do not apply the theorem, and then he said it's just a foundation. I am to apply this work in photometry, hypothesis. So I have a way to estimate masses using photometry. I did this just to know what I have to expect on the splashback radius. But that's all.
Lucas, go back. You didn't show us, but this is the worst plot I ever saw. What kind of calibration are you using? Is it X-ray? No, with lens.
We got
And then with X-rays, you all get something so bad.
the X-ray that I have is using photometry last year in the graduation. That was better than this.
So it's very bad.
Yes.
You need to understand it better. Because there are previous results are much better.
Yes, that one was using photosys, and I think that it's because I have a lot of clusters in redshifts like 0.3 and greater. And in these clusters, the profiles are a little bit noisy because as the sets doesn't observe them really well. So using photometry, the clusters are really, they have a more silent noise. And the spectral radius is better determined in the
So what's the idea? Using just photometry, you can estimate the splashback radius, and using calibration, you can then estimate the cluster.
I think I remember in the Dark Energy survey, there are some words about splashback radius by the guy is Wolf Jenny. Actually, Lucas Sequity was in. No? I think so. At some point. So it's photometry. So like, I don't know exactly. Of course, I don't know the details.
One curiosity, do you have access to any other information like star formation rate, some other what? No. Chemical
We
composition?
can have, but
No, it's not enough.
it isn't, it's not about that yet.
That's really important because something that we want to do is cluster cosmology. We need the so this proxy.
Arguably cosmology. What if?
The number counts, cluster counts, depends on cosmology. So how many clusters you have, how many clusters will given mass and given redshift, that depends on cosmology. So that's the bridge.
So omega lambda in particular.
Omega lambda, sigma 8, and the growth of the perturbation.
Okay.
So
It's not really late time, so omega lambda is very important, I guess.
omega lambda, but also, yeah, sigma 8, and the radius does not matter. So what matters is the mass. So it's the mass as a function of redshift. So it's the number, how many clusters with given mass and given redshift. Of course, they're models, they're cosmological models for this. If you have, for instance, some different dark matter that can suppress structure formation that will affect.
No, but wait, I have not checked. So, but once the system is gone nonlinear, so it decouples from the cosmological expansion, no?
Yes.
So what matters, because cosmology matters as long as it goes, so it affects when it goes on linear, basically, when we start visualizing. So once it visualizes, cosmology doesn't matter anymore.
No, but the mass that ends up in there is a reflection of the initial conditions.
Yeah.
That's how cosmology gets. And also the positions where they are relative to each other. They are close correlation.
So this mass function, so just to get back a little bit, student, into our question. Depend on, you can actually try to model these mass functions using cosmology, and there's something called the spherical collapse model, which actually gives you a model for the mass function, and that depends on cosmology. Even though it's a linear regime, okay, there's a relation between the linear and nonlinear regimes in the spherical collapse models. So that's why it's important. That is the chair. So we have to thank the speaker.
Oh,